Okay, good day. So we will discuss lesson 4.2 or the precision of indirectly determined quantities. So as expected, so at the end of the discussion, the student must be able to first identify data precision of determined quantities, and second one is able to solve the errors from the covariance matrix. Okay, so what are the estimated errors, no, given that we have this matrices, from the observations from their coefficients, then we have your covariance matrix, then we identify the errors, no, estimated errors after the adjustment. So following an adjustment, it is important to know the estimates errors in both the adjusted observations and the derived quantities. So ideally, before the adjustments, no, you have this, what we have is called the concept of signal and noise. No? So your measurement consists of these signals and this noise. No? So literally, your measurement contains what we call the physical quantity and the measurement error. No, so ideally, before the adjustments, you've conducted series of measurements. Let's say for a specific line, you measure it 10 times, then you have your standard deviation after the adjustments, or you can have the uh, you have your presumed, or let's say the expected error before the adjustment. So no, there are some things that we need to identify, like the a priori, meaning to say before adjustment errors, then a posteriori, the after adjustment errors. No, so we must be able to identify those two so that we can at least think that okay, we will use this uh, or this error are valid or is valid, no, for the as our reference variance, no. Okay, so for example, after adjusting the level nets, no, as previously discussed or you've been studying, no, the uncertainties in both adjusted elevations, the adjusted elevation, you have your observation, like I have this elevation at this point, no, but this is derived from a certain reference model or reference, and you have your computed benchmark or computed elevations, no. So the uncertainties or the statistical or the errors, no, should be computed, no, after the adjustment, no. So error propagation formulas were developed for indirectly measurement or measured quantities which were functionally related to observed values. So in your previous course, that the before the geodetic computation and adjustment, of course, you have your theory of errors. No, this is that is where it is discussed the error propagation, right, of certain measurements. Usually in surveying, we have plenty of indirect measurements. So when we say indirect measurements, we determine that point or that position, or let's say position, indirectly, meaning to say we don't observe that point directly, but we obtain that position from different models. No, you can say triangulation, trilateration, and so on, no? So on and so forth. So next, we will have the development of the covariance matrix. So remember, we have the uh, we have this equation involving weight. So here we have this your weight. the coefficients, then the unknowns. Okay, then you have your observation matrix, then your residuals. Okay, so least square solution of the weighted observation equations is given by this equation. So for unweighted least squares, so you just remove the weight matrix. Okay, so remember that X contains the most probable value for the unknowns. Right? So X contains the most probable value for the unknowns. Okay, so if you can check revisit the equation or the formula, so that is okay. Okay, that one, no, the normal equation. So here we have this equation. This serves as your true value, and here this delta x is somehow the true value, or which is the true value differ from x by a small amount. So this is somehow a small amount, no? In general, given that your observation data, your sets of data are free from biases and errors, though, or systematic errors, though there are no observations that are perfect, so tendency there'll be small deviations of your most probable value compared to the true value. So we have this delta x, which is somehow a small amount, which represents the errors in the adjusted values. No? So even though you already adjusted your observation or uh, your data, so still uh, it has a small amount of error. No? So technically, derived from your true value, you have this small amount of error. So usually in our least square solutions, we obtain the most probable value that will give us a summation of your residuals or error into a minimum amount. Mean to say, this adjustment serves as the best or the as much as possible that will lead us to a smaller amount of error, the summation of those error. No, always keep in mind that in surveying and your observation, it is a series observation. The error propagates. No, so especially if your observation contains angular observation, distance observation, and other kinds of observation, but then uh, this the least square solution will provide us a best estimation. No, sometimes the least square solutions provides provide us an estimation or assumption, or as they say, the most probable value. Okay, so now let's consider a small amount of increment change of or let's say delta L, or in the measured values L, which changes X to its true value. Diba? If you can remember, you have this uh, uh, your L, or your observation value, to obtain to your true value. Diba? You have your residual. Diba? So that's your somehow your true value, but that's not the true value, but it's only your estimate or assumption. So following the equation, um, we arrive at this uh, value. And So delta L serves as the errors in the observations. And the equation can be rewritten as delta X, this one, okay? Or this one can be converted into the what we call the residual, okay? Then we rewrite B is equals to so delta X becomes BV, okay? Then multiplying transposes, no? We have delta X times delta X transpose is equals to BV times, okay, BVT. Then we have this matrix property. So delta X times the transpose of delta X is equals to B times V times V transpose times B transpose. No? Then this happens. Okay. So kindly observe the equation. This one. So let's just skim this part. So we have the expanded equation of the this one of the B V V T B T, and this is the expanded equation of your uh, delta X times delta X, or the transpose matrix of delta X. Okay. So assume that it is possible to repeat the entire sequence of observation many times, then you have your A. No. So this serves as how many times your observation. So given that if a large, or if the observation, number observation, which is A, no, the number of observation is quite large, the terms in the previous equations are the variances as defined. So we have this uh, matrix, no? So then a considering a number of sets of observations, then we have this one. So let's say A times, and that each time a slightly different solution occurs, then yielding a different sets of X. Okay. Then recognizing the diagonal terms as variances of the quantities observed. So this equation, the variance of the off-diagonal terms, when we say off-diagonal terms, as the covariances. No? So meaning to say this is your diagonal, then you have your off-diagonals here. No? And the fact that the matrix is symmetric, the equation can be rewritten as this one. Okay. So to compute for your the estimated standard deviation for any unknown parameter computed, meaning to say after uh, could be after the adjustment or before adjustment. So for any unknown parameter computed from a system of observation equations is expressed as in this equation, where Q is the diagonal element. Okay, so Q is the diagonal element. So where do we get Q? So if you can remember, Q is N or ATA 1. So the diagonal elements, okay, so you have the from the ith row and the ith column, okay. So when we say where do we get this one? So you have your uh the covariance matrix, no? Okay. So from your covariance matrix, which is equals to the inverse of the normal matrix of the normal equations. So again, since the normal equation matrix is symmetric, its inverse is also symmetric, and thus the covariance matrix is a symmetric matrix. Okay, so let's proceed to the example. So the reference variance of an adjustment is 0.89. Okay, so the covariance matrix and a known parameter matrix are this one. So what are the estimated error in the adjusted value for A, B, and C? Okay, so for example, we have this given value of 0.89 as your reference variance of an adjustment. So when you say reference variance, no, it's still in squared, right? So you need to determine its uh, the somehow the error or standard deviation. No? Okay, so that would be square root of 0.89, that is 0.94. Okay, so 943. Okay, so let us put it in that way. Okay, so to determine the estimated standard deviation of the unknown parameters, no, A, B, C, diba? In least squares, we determine what are the best estimate of A, B, and C. So here, we will try to determine what are the estimated error of the adjusted value A, B, and C. So think about with this example that you have your error prior to adjustment, then technically you will have an error after the adjustment. Okay, so technically you have your observed, the most probable value of A, B, and C, and they have also corresponding errors after adjustment. So errors achieved or obtained in the adjustment or in the determination of parameter A, B, and C. So to determine for the estimated error, so you have this equation as sub A for A is equals to the reference standard deviation of the adjustment times the square root of the Q matrix of AA. So here, that would be plus or minus 0.943 times the element QAA. So where is QAA or Q sub AA? So remember, you need to get only the diagonal components. of the Q matrix. So this is your QAA. This is your QBV and QCC. Now, uh, small letter QCC. Therefore, that would be 0.5486. Then this is equivalent to 0.943 times the square root of 0.5486. So the estimated error for the parameter A is 0.698. Then to solve for B, that would be, again, using this equation, is equals to plus or minus 0.943. So this, again, this is plus or minus square root of 0.4987 is equals to plus or minus 0.6659 or 666. No? And for S sub C, it will be S sub O square root of Q C C is equals to plus or minus 0.943 times square root of 0.8439 is equals to plus or minus 0.866. So therefore, the estimated error in the adjusted value for A, B, and C. So you have for A, and we have for B, and we have for C. So this is how you solve for the estimated error of the adjusted values from your least square solutions.